Welcome, everyone. Today, we will understand the combined dynamics of an electric vehicle, with special focus on dynamic load transfer. We will study a rear-wheel drive electric vehicle negotiating a turn. This problem brings together turning analysis, force calculation, and friction limits in one complete picture. We will see how weight shifts during motion, how tire forces are generated, and how the friction limit controls available grip. By the end, you will clearly understand how load transfer and friction together decide stability, traction, and safe cornering performance of an electric vehicle. In this problem, we analyze a rear-wheel drive electric vehicle undergoing combined cornering and acceleration. The vehicle has a mass of 1,800 kilograms and a wheelbase of 2.8 meters. The center of gravity height is 0.55 meters, and the track width is 1.6 meters. The road tire friction coefficient is 0.9%, representing a high grip surface. The vehicle is steered at 5 degrees, travels at a constant speed of 18 meters per second, and simultaneously accelerates at 1 meter per second squared. All resistive forces, including aerodynamic drag and rolling resistance, are considered. Motor specifications are included to ensure the demanded torque is realistic and within EV operating limits. These parameters fully define the vehicle and operating condition needed to evaluate forces, load transfer, friction usage, and stability limits during combined maneuvering. In this step, we link steering input to vehicle motion. Using the bicycle model, the turn radius is computed as wheelbase divided by steering angle, that is, R equals L over delta, giving a turn radius of 32.1 meters. Next, lateral acceleration is calculated from longitudinal speed squared divided by turn radius, resulting in 10.1 meters per second squared. This shows how steering geometry directly sets the curvature of the path and the lateral acceleration the vehicle must generate during the turn. Next, we calculate the forces that resist the vehicle's motion. First is aerodynamic drag given as 143 newtons. Second is rolling resistance given as 212 newtons. Both aerodynamic drag and rolling resistance act opposite to the direction of motion, reducing the effective force available for acceleration and shaping how the vehicle responds at higher speeds. To keep the vehicle accelerating, the rear wheels must overcome inertia and resistive forces. First, we compute the required rear longitudinal force. Required force, Fx rear, is equal to mass times longitudinal acceleration plus aerodynamic drag plus rolling resistance. Substituting values gives 2,155 newtons. Next, we check whether the motor can supply this force. Available traction from the motor is motor torque divided by wheel radius. This evaluates to 7,813 newtons. Since available motor force is much larger than the required force, the motor is not the limiting factor. The true constraint comes from tire grip and friction, not motor capability. Now we look at how weight shifts during motion. First, longitudinal load transfer happens because of acceleration. It is calculated as delta Fz longitudinal equals mass times longitudinal acceleration times CG height, divided by wheelbase. For this vehicle, that gives 354 newtons, which is added to the rear axle during acceleration. Next, lateral load transfer happens during cornering. It is calculated as delta Fz lateral equals mass times lateral acceleration times CG height divided by track width. This evaluates to 6,240 newtons, shifting load from the inner wheels to the outer wheels. Together, these transfers do not change total weight, but they redistribute normal force across the tires, directly affecting how much grip each tire can generate during combined acceleration and turning. We have now understood how acceleration redistributes tire loading, both longitudinally and laterally. Longitudinal acceleration shifts load between the front and rear axles, while lateral acceleration during cornering transfers load between the left and right tires. Together, these effects determine how much grip each tire can generate and directly control traction, stability, and steering response. The rear axle lateral force, called FYR, is obtained from the lateral force balance and lateral moment balance equations of the vehicle. Using these balance relations, the rear lateral force is written as FYR equals mass multiplied by lateral acceleration multiplied by A, divided by the wheelbase length L. In words, This means the rear axle carries a portion of the total lateral force based on how far the vehicle's center of gravity is located from the front axle. Finally, the rear axle lateral force share is defined as the distance from the front axle to the center of gravity, divided by the total distance between the axles. This shows that vehicle geometry alone decides how lateral force is split between front and rear tires during cornering. Now let us calculate the rear axle lateral force. Fyr, which equals 7,800 newtons. Next, let us determine the rear normal load, Fzr, which equals 7,920. 2 newtons. We shall now compute the maximum friction force available at the rear axle. This is mu multiplied by Fcr, which gives 7,130 newtons. To check feasibility, apply the friction ellipse condition. The combined force must satisfy Fxr squared plus Fyr squared less than or equal to mu Fzr squared. Here, Fxr squared plus Fyr squared equals 1.1, 2 times 10 to the power 8, which is greater 7,130 squared. This means the condition is violated. So we can conclude that the rear tires are saturated and the demanded combination of drive force and cornering force is physically infeasible. This clearly shows how combined acceleration and cornering can exceed tire friction limits even when each force alone appears acceptable. To find the maximum lateral force the rear axle can support, we use the friction ellipse. Fyr max equals square root of mu times Fzr squared minus Fxr squared. Substituting values, we get Fyr max equals 6,810 newtons. Next, we compute the maximum achievable lateral acceleration. A y max equals Fyr max divided by mass times 0.429. Substituting numbers, a y max equals 8.83 meters per second squared. Finally, we calculate the actual turning radius limited by tire friction. R actual equals v squared divided by a y max. Substituting values, R actual equals 36.7 meters. To conclude, we say, even though steering geometry predicts a tighter turn, rear tire friction limits the vehicle, forcing a larger actual turn radius. This proves that tire grip, not steering angle, ultimately controls vehicle cornering performance. Let us summarize the 3 core equations that govern vehicle cornering under combined acceleration. First, we relate turn radius to lateral force. R equals m times v squared divided by Fy. This tells us that for a given speed, higher lateral force means a tighter turn, while limited force increases the turn radius. Second, we introduce the friction ellipse, which limits available lateral force when longitudinal force is present. Fy equals square root of mu times Fc squared minus Fx squared. This shows that braking or acceleration consumes friction, reducing lateral grip. Finally, combine both ideas into a single governing equation as shown below. These equations together prove that vehicle path is not set by steering alone. It is jointly controlled by mass, speed, friction, load transfer, drag, and acceleration demand, forming the mathematical backbone of real-world vehicle dynamics. When the vehicle accelerates, part of the tire's available friction is used to produce longitudinal force. This reduces the friction left for cornering, so the maximum lateral force drops. As a result, the vehicle cannot follow the tight turn radius predicted by steering geometry alone. Instead, the actual turn radius becomes larger because lateral grip is limited. In simple terms, a tire cannot give full acceleration and full cornering at the same time. This limitation is captured by the friction ellipse, which shows that longitudinal and lateral forces must share the same friction budget. The key takeaway is the vehicle must trade acceleration for cornering, and this trade-off defines the true physical limits of vehicle dynamics, regardless of motor power or steering input. Now, let us analyze a rear-wheel drive vehicle taking a turn at constant speed. Since speed is constant, there is no acceleration or braking, only lateral motion due to steering. The vehicle experiences yaw rotation and side forces at the tires, generated by tire slip angles. Front and rear tires do not produce equal forces. This imbalance determines whether the vehicle understeers, oversteers, or remains neutral. By studying lateral tire forces, yaw rate, and force distribution, we understand how RWD vehicle maintains cornering stability and how design choices in tires, geometry, and mass distribution influence handling behavior. In this problem, we study a rear-wheel drive vehicle negotiating a constant speed turn. The goal is to analyze tire forces and check friction limits during steady cornering. The vehicle has a mass of 1,600 kilograms and a wheelbase of 2.8 meters. Its center of gravity height is 0.55 meters, and the track width is 1.6 meters. The car travels at a constant speed of 18 meters per second while following a turn radius of 40 meters. The road tire friction coefficient is 0.9. We assume steady-state cornering, meaning speed is constant, and longitudinal acceleration is 0. Tires are modeled as linear, with no aerodynamic forces included. The vehicle uses an open rear differential with symmetric geometry on both sides. These assumptions simplify the problem so we can focus purely on lateral force distribution and friction limits during a constant speed turn. First, we calculate how strongly the vehicle must accelerate sideways to follow the turn. Lateral acceleration is found by saying vehicle speed squared divided by turn radius. So, this gives a lateral acceleration of 8.1 meters per second squared. Next, we calculate the total lateral force needed to keep the vehicle on this curved path. Lateral force equals vehicle mass multiplied by lateral acceleration. So, this gives a required lateral force of 12,960 newtons. This shows a key relationship: higher speed or a tighter turn radius demands more lateral force, which must be supplied by tire grip. If the tires cannot generate this force, the vehicle will slide outward instead of following the turn. Now we estimate how much sideways force the rear axle must carry. Assuming the car shares cornering evenly between front and rear, the rear axle takes half of the total lateral force. So the rear lateral force, FYR, equals 6,480 newtons. Next, we calculate the static normal load on the rear axle. This found using the formula FZR static equals mass times gravity times distance from the center of gravity to the front axle divided by wheelbase. Substituting the values gives 7,848 newtons on the rear axle. Since there are two rear wheels, each rear wheel carries 3,924 newtons. This step shows how weight distribution directly sets the grip available at the rear axle, even before any load transfer occurs. Let us calculate the lateral load transfer at the rear axle, which is the most important step in wheel level force analysis. Lateral load transfer is found by saying rear lateral force multiplied by center of gravity height divided by track width. Substituting the values gives a rear axle load transfer of 2,227 newtons. This load moves from the inside rear wheel to the outside rear wheel. The total rear axle load does not change, but how it is shared between the two wheels changes dramatically. This step is critical because tires generate force individually, not as an axle. Once load shifts, the outside tire gains grip while the inside tire loses grip, directly affecting stability and cornering limits. The lateral load shift is defined as the difference between the load at the outside rear wheel to the inside rear wheel. Physics preserves balance, so lateral load transfer is treated as a redistribution. Half of the computed load transfer is added to the outside wheel, half is subtracted from the inside wheel. This way, the net lateral load transfer across the axle is still the same. It is simply shared equally in magnitude but opposite in sign between the two wheels. The equation also reveals two key design influences. Higher center of gravity height increases load transfer. Wider track width reduces load transfer. This is why low battery placement and wide stance are essential for stable, high-performance vehicles. We shall now determine how the rear axle load is split between the two wheels after lateral load transfer. The outside rear wheel gains load, while the inside rear wheel loses load. The outside rear wheel normal load is 5,038 newtons, and the inside rear wheel normal load drops to 2,810 newtons. Next, we calculate the maximum lateral force each rear wheel can generate. This comes from the friction limit rule, spoken as lateral force must be less than or equal to friction coefficient times normal load. For the outside rear wheel, multiplying 0.9 times 5,038 gives a maximum lateral force of 4,534 newtons. For the inside rear wheel, multiplying 0.9 times 2,810 gives a maximum lateral force of 2,529 newtons. This result clearly shows that lateral load transfer creates unequal grip between the two rear wheels. The outside tire becomes the dominant force carrier, while the inside tire approaches saturation first, an effect that strongly influences cornering stability and limits overall vehicle performance. Now we check whether the vehicle can safely negotiate the turn. First, we identify the maximum lateral force the rear axle can generate. This is the sum of the maximum forces from both rear wheels, giving 7,063 newtons. Next, we compare this with the required rear axle lateral force, which is 6,480 newtons. Since 6,480 is less than 7,063, the available tire grip is sufficient. In conclusion, the rear tires are not saturated, and the vehicle can successfully negotiate the turn under the given conditions. This feasibility check confirms that cornering performance is traction limited but stable, validating the vehicle setup and assumptions. If lateral load transfer is ignored, both rear wheels appear identical. Each wheel carries 3,924 newtons of normal load and can generate 3,532 newtons of lateral force. Together, this suggests a total rear capacity of 7,063 newtons. But this picture is misleading. In reality, lateral load transfer makes the outside wheel heavily loaded and the inside wheel lightly loaded. The inside wheel therefore sits much closer to its friction limit and will lose grip first, especially if any longitudinal force is added during acceleration. This is why vehicle instability begins at a single wheel, not across an axle. Ignoring load transfer hides the true saturation mechanism and leads to unsafe predictions. Hence, lateral load transfer analysis is mandatory for wheel-level force calculations, traction-limited cornering, and accurate stability and control system design. The key insight from this analysis is simple but powerful. Lateral load transfer does not change how much lateral force the vehicle needs, but it decides which wheel reaches its limit first. During cornering, the total lateral force demand stays the same, set by vehicle speed and turn radius. However, lateral load transfer redistributes normal load between the inside and outside wheels. The outside wheel becomes heavily loaded and carries most of the force, while the inside wheel becomes lightly loaded and is the first to lose grip. A clear diagram helps visualize this effect. Vertical load shifting from inside to outside wheel, unequal tire force vectors, and a comparison between required lateral force and maximum available friction force at each wheel. This explains why vehicles lose stability wheel by wheel, not axle by axle. It also shows why electronic stability control, torque vectoring, suspension tuning, and track width design all focus on managing load transfer rather than eliminating it. In practice, good vehicle dynamics design delays wheel saturation, improves predictability, and converts available tire friction into usable performance instead of instability. Let us summarize how we obtained the solution. First, we calculate the required lateral force needed for the vehicle to follow the turn. This comes from the centripetal force relation, spoken as lateral force equals mass times speed squared divided by turn radius. Second, we compute the lateral load transfer at the rear axle. This is obtained by taking mass times lateral acceleration times CG height divided by track width, showing how cornering shifts load from the inside wheel to the outside wheel. Third, using this load transfer, we determine the normal forces on the inside and outside rear wheels. The outside wheel gains half the transferred load while the inside wheel loses the same amount. Fourth, we compute the maximum lateral force each rear wheel can generate. This is found by multiplying the friction coefficient by the normal force on each wheel, spoken as mu times Fc. Finally, we compare the required lateral force with the maximum available tire force. If the available force is greater than the required force, the vehicle can safely negotiate the turn. If not, the rear tires will saturate and the vehicle will lose stability. Let us attempt another problem where we study the dynamics of a rear-wheel drive vehicle when it is turning and accelerating at the same time. The rear tires must generate two forces together, a longitudinal force for acceleration and a lateral force for cornering. Tire friction is limited. The total force at the tire cannot exceed the friction limit, which depends on the normal load and road grip. When more force is used for acceleration, less force remains for cornering, and vice versa. Dynamic load transfer increases rear axle load during acceleration, helping traction, but it does not remove the friction limit. If the combined demand exceeds this limit, the the rear tires lose grip, leading to wheel spin, understeer, or oversteer. This analysis shows how vehicle stability, steering response, and usable motor torque are all governed by the interaction of load transfer and friction limits. In this problem, we analyze a rear-wheel drive vehicle undergoing steady-state cornering with constant longitudinal acceleration. The vehicle has a mass of 1,600 kilograms and a wheelbase of 2.8 meters. The center of gravity height is 0.55 meters, and the rear track width is 1.6 meters. The distance from the center of gravity to the front axle is 1.4 meters. The vehicle travels at 18 meters per second while negotiating a turn radius of 40 meters. A constant longitudinal acceleration of 2 meters per second squared is applied. The tire road friction coefficient is 0.9 and gravity is 9.81 meters per second squared. The following assumptions are made. The vehicle is in steady-state cornering, tires behave linearly, the rear differential is open, aerodynamic forces are neglected, and the lateral force is shared equally between front and rear axles. These parameters and assumptions fully define the problem setup for the subsequent force, load transfer, and feasibility analysis. First, calculate lateral acceleration as speed squared divided by turn radius, which gives 8.1 meters per second squared. Next, compute total required lateral force as mass times lateral acceleration equals 12,960 newtons. Assuming equal front-rear sharing, the rear axle carries half of this demand. So the rear lateral force FYR equals 6,480 newtons. Let us calculate the static normal load on the rear axle. This is found as mass times gravity times distance from the front axle to the center of gravity, divided by the wheelbase. Substituting values gives a rear axle load of 7,848 newtons. Since the rear axle has two wheels, the static load is shared equally. Each rear wheel therefore carries 3,924 newtons. This static load forms the baseline grip level before any lateral or longitudinal load transfer occurs. We calculate the longitudinal load transfer during acceleration. This is given as 628.6 newtons. This load adds to the rear axle, increasing its normal force, so the rear axle normal load under acceleration becomes 8,476.6 newtons. Before any lateral load transfer occurs, this rear axle load is shared equally. Each rear wheel therefore carries 4,238.3 newtons. Key point is that the longitudinal acceleration increases rear axle grip, allowing the driven wheels to support more traction and cornering force before reaching the friction limit. Lateral load transfer describes how weight shifts during a turn. The rear lateral load transfer is calculated as delta Fz, rear lateral, equals Fy, rear times h divided by t, which gives 2,227 newtons. This load shift increases the normal load on the outside rear wheel to 5,351.8 newtons and reduces the load on the inside rear wheel to 3,124.8 newtons. This shows how cornering transfers load from the inside wheel to the outside wheel. The maximum friction force at each rear wheel is calculated as Fmax equals mu multiplied by Fz. For the outside rear wheel, the maximum friction force is 4,816.6 newtons. For the inside rear wheel, it is 2,812.3 newtons. The required longitudinal force at the rear axle is Fx rear equals m multiplied by x, which equals 30,200 newtons. With an open differential, each rear wheel provides Fx wheel equals 1,600 newtons. The lateral force per wheel is Fy wheel equals 6,480 divided by 2, which equals 3,240 newtons. We now perform the friction ellipse check for the inside rear wheel, which is very essential. The required force is 13.06 times 10 to the power of 6. The available friction force is 7.91 times 10 to the power of 6. Comparing the two values, we find that the required force exceeds the available friction force the inside wheel saturates. This confirms loss of traction at the inside rear wheel. We check whether the vehicle can safely negotiate the turn. First, we identify the maximum lateral force the rear axle can generate. This is the sum of the maximum forces from both rear wheels, giving 7,623 newtons. Next, we compare this with the sum of required rear axle lateral force and the rear axle longitudinal force, which is 9,680 newtons. Since required rear axle lateral force is greater than the maximum lateral force, the rear axle can generate the available tire grip is insufficient. In conclusion, the rear tires are saturated, and the vehicle cannot successfully negotiate the turn under the given conditions. This feasibility check confirms the same. When both lateral and longitudinal load transfer are considered, the inside rear wheel exceeds its friction limit. As a result, the inside wheel will spin or slide. Because the vehicle has an open differential, the rear axle force is limited by this least loaded wheel. This means the vehicle cannot maintain the required turn radius while accelerating at 2.0 meters per second squared. In summary, the combined effects of cornering and acceleration create a critical failure condition at the inside driven wheel. Longitudinal load transfer increases grip at the rear axle during acceleration. At the same time, lateral load transfer reduces grip at the inside rear wheel during cornering. The friction ellipse shows that longitudinal and lateral forces are coupled, not independent. As lateral force demand increases, less force is available for acceleration. Because of this coupling, the inside rear wheel becomes the limiting factor. Visually, the friction ellipse is exceeded first at the inside wheel. The load transfer diagram shows reduced normal force, and the force vector plot shows combined forces reaching the limit. The final insight is, acceleration while cornering is limited by the least loaded driven wheel. The inside rear wheel is the bottleneck. In this study, we analyzed the combined dynamics of a rear-wheel drive electric vehicle during cornering and acceleration. By including both lateral and longitudinal load transfer, we observed how vehicle weight shifts dynamically between wheels. Because tire forces are limited by friction, the inside rear wheel reaches its friction limit first. The friction ellipse concept clearly demonstrated that lateral and longitudinal forces are coupled, and increasing one reduces the available capacity for the other. As a result, the inside rear wheel becomes the limiting factor for traction. This leads to wheel slip, limits the effective rear axle force due to the open differential, and prevents the vehicle from maintaining the desired turn radius while accelerating. Vehicle stability, traction, and safe cornering performance are governed by load transfer and friction limits, with the least loaded driven wheel determining the maximum achievable performance. Thank you all for your patience. We will meet again to explore another topic in electric vehicle powertrains.